Okay, so today we're going to talk about implicit differentiation. So implicit differentiation is basically a type of differentiation that differentiates the entire expression, so it's especially useful. It is used in a variety of circumstances, but it's mostly used when the dependent variable y cannot be isolated. So the procedure for this is we want to differentiate both sides with respect to x, so d over dx, and then solve the equation for dy over dx, just noting that dx over dx equals 1, which is just x differentiated by x. If x and y are multiplied or divided, we want to use the product or quotient rule. And of course, we can use any normal algebra or differentiation rules, including the chain rule if we need to. And then the final step is we want to replace y in the differentiation with the original expression so that there is no or minimal y in the derivative, in the final derivative. So we also want to look a little bit at inverse derivatives. So an inverse function is just one where if you have a function, then you switch x and y, that is the inverse of that function. And if f of x is a one-to-one differentiable function, then its inverse function f inverse of x is differentiable, and the derivative for that is 1 over f prime of the inverse of x, so long as that denominator is not 0. So first we want to determine that the function is one-to-one. So a one-to-one function is just one where each x value has a unique y value and vice versa. Then we want to find the inverse function, so switch x and y, and we want to use the formula to find the derivatives at that point. There's also logarithmic differentiation, so this is how we differentiate logarithmic functions. So the basic one is just log of a argument x. The derivative of that, the first derivative, is 1 over x ln a, ln being the logarithm of e, so the natural logarithm. Similarly, ln x, the derivative of that is excuse me, just 1 over x. And then for composite functions, we just use the chain rule. And a change of base is sometimes useful when we want to change the base of a logarithm. So we can say log a of x is equal to ln x over ln a. There are also a few other cases which we won't look at in too much detail, but they're there if you need it. And just noting that last case, if you have a function exponent with an exponent of another function, then we want to use logarithmic differentiation, which we will talk about next lesson. So first we're going to go over a example of implicit differentiation, and then we're going to go through an inverse differentiation. And for the extra examples in the description below, we'll solve for logarithmic differentiation and another implicit differentiation. But for now, we'll just start with these. So for our first question, we have x squared plus x squared plus 3xy minus 4y squared. Want to find y prime, which is dy over dx. So we're going to use implicit differentiation. So what we want to do is differentiate both sides with respect to x. So d over dx, and I just want to highlight this as the derivative with respect to x. So that'll come into effect a little bit later. We'll talk about that a bit more. So we'll do this side, x squared plus 3xy minus 4y squared. And then same on the other side, d over dx. Oops, should have said this is equal to 3. That's what it was in the original, in the PowerPoint. So then we're going to differentiate. So derivative of x squared is 2x dx over dx. And so what that dx over dx is saying is that we're differentiating the variable x with respect to x. Now, just following algebra, we know that this cancels out and is equal to 1. If you have the same thing on the numerator as the denominator, it's equal to 1. And then we're going to use the product rule. So if we differentiate 3x, that'll just be 3 dx over dx times y plus 3x dy over dx. So again, just keeping those dx over dx and dy over dx in is very important, just so we don't get confused. And again, this will cancel out to 1. And then we have minus 8y dy over dx equals 0, just because any derivative of a constant is equal to 0. So hopefully that makes sense. Again, I can't emphasize enough how much you should leave in that d over dx part, so the dx over dx or dy over dx. Just it makes it a whole lot simpler. I've seen some people do instead of dy over dx, they'll write y prime, but I find I make a lot of mistakes when I do that. So I'll just write this in with the simplifications that we made. So 2x plus 3y plus 3x dy over dx minus 8y dy over dx equals 0. And then we just want to isolate for that dy over dx. So we have 3x dy over dx minus 8y dy over dx is equal to negative 2x plus 3y. And then taking the factor out, and just isolating. And then finally, we want to replace y with the original expression. So in this case, we don't have a y equals anything. So it's not, for example, y equals x squared plus 3xy minus 4y squared. So then we can't do that final step. So this is how we have to leave it. So that is the derivative using implicit differentiation. So it's just sort of basic algebra, but it does take a little while took a while for me to wrap my head around anyway. All right, then we're going to do inverse. So we have the function 2x squared plus 4x minus 3. Now this is a quadratic function, so it's likely not 1-to-1. But for this case, it should work out for us. So what we want to do first is we're going to define the inverse function. So let's say this equals y. So just flip x and y. So 2y squared plus 4y minus 3 equals x. Excuse me. And we know that x is 13. That's stated in the PowerPoint. So I'll just put this up here. So then 13 equals 2y squared plus 4y minus 3. Excuse me. And I'm just going to solve by inspection. We know that for this y equals 2 because, well, I mean, if you put in 2, that's 2 times 2 times 2 is 8 plus 4 times 2 is 8, so 16 minus 3 is 13. All right. And then, excuse me, sorry. We're going to put it in the derivative. So for that, it's the inverse of x is equal to 1 over f prime of f negative 1, the inverse of f of x. So we need to solve for these parts. So we know that f negative 1 at, x equals 13 is equal to 2, and that was what we just solved for a few moments ago. And then we want to find f prime at 2. So just a reminder, f of x equals 2x squared plus 4x minus 3. So then f prime of x equals 4x plus 4, and f prime of 2 is 4 times 2 plus 4, which is equal to 16 plus 4 is 20. So then we have basically solved it. So I can say therefore inverse of f, derivative of it, is 1 over 20 at x equals 13. So that's all for today. Again, you can go into the description for the annotated version of this and the annotated version of the other examples, the extra example. And thank you again to Loom and Google Keep, and as well to my professors. And I hope to see you again soon.